Hi everyone, welcome to lecture 11 in the series of business analytics course. In this lecture, we are going to review week 6, which is basically containing multiple linear regression. So without further ado, let's just get started. So here you can see that week 6 is going to have multiple linear regression. What are the topics which we are going to cover? First, we are going to introduce and then how do we interpret this thing. Then we are going to see adjusted R square, very important topic. Then partial and marginal slope, what is the difference between them? Path diagram, how do we use them? And then multicollinearity and variation inflation factor, which is abbreviated as VIF. So this is how your multiple linear regression looks. You have already seen linear regression in week 4, and I have already explained that regression is used for predicting something which is continuous, right? So when you want to predict a continuous variable, we use regression. And in linear regression, we take linear combinations. That is why it is known as linear regression. In week 4, we studied simple linear regression. Why it was simple? Because you are only having one input variable, or you can say one explanatory variable, right? So we were restricting ourselves to y is equals to beta naught plus beta 1 x1, right? So that is why it was a simple linear regression, because you were only having one input variable. But it is very obvious that in real life, it would never happen that the variable which you are trying to observe, the response variable, it only gets affected by one thing, right? In general life, anything has multiple causes. So to model such situation, we have multiple linear regression. In multiple linear regression, instead of just having one explanatory variable, we will have multiple explanatory variable. And as you can see this equation, this is what multiple linear regression would look like. Y is your response variable, or you can say dependent variable, or you can say explained variable. And x1, x2 up till xn, these all variables are your predictors, right? These are independent variables, or you can say explanatory variable, right? So this is what we have, and these are the coefficients. So basically you combine these coefficients with your variables, and then how this is how you will predict this thing. And this epsilon is basically the random noise which you have here. So the idea is your population. Let's say I have 10,000 people and they are following a linear trend, right? But in real life, I will not have access to all these 10,000 people. So I will take out the sample, let's say 100 people, 200 people, or 500 people, some sample, and then I will try to make a model. And using these 500 people, I would try to predict the original model, or you can say the original trend in the uh, entire population. So this is what linear regression does. Basically, instead of taking entire population, you have access to some samples, and using that samples, you try to predict these things, beta 1, beta 2, beta naught, and all that stuff. You try to predict them so that you can combine and then you can proceed further. So first we should know how do we interpret beta 1. So whatever you will have here, these beta i's, let's say beta 1 is corresponding to x1, beta 2 is corresponding to x2, and so on and so forth. So whenever there would be a question, how do we interpret beta 1 and all that stuff, you should understand that if we change xi, whatever variable you have predictor variable, by 1 unit, then y, which is basically the one which you are trying to predict. So xi is your explanatory variable, y is the variable which you are trying to predict. So if I change my xi, let's say x1 by 1 unit, then y would change by beta 1, given that other variables are constant. So this is the important part, other variables are constant. This is very important. And what you should remember is, if I change, xi by 1 unit, y would change by beta 1. But if I only take all other things as constant, so I am not allowing x2, x3, x4, and up till xn to change. I'm only saying I'm only allowing x1 to change. So when I allow x1 only to change, then y would change with respect to beta 1. So if I have, 1 unit change in x1, then y would also increase by beta 1 amount. So this is what we interpret. If I reduce x1 by 1 unit, then y would reduce by beta 1. So this is how you interpret, and you can obviously see this thing that beta 1 is nothing but del of y, partial of y with respect to partial of x1. So that is why it's the situation. All other input variables x2, x3, x4 are assumed to be constant. So always remember that in your multiple linear regression, beta I is going to be the change in y, given you change 1 unit in the corresponding explanatory variable, assuming all other variables are constant. This is very important because this line have been used to trick a lot of students in MCQ based questions. So always remember that it assumes all other explanatory variable were constant. Okay, so this is what we have in the multiple linear regression, and then we will see adjusted R square. So we have already seen R square. R square is basically a way to quantify how much is my model good. It's a metric to quantify our goodness of model, and this R square is basically going to tell you how much you can explain the variability in Y, right? Explain variability in Y using your X variable. So this is what you have, right? In simple linear regression, this is what we can say, that if I'm making a model like Y is equals to beta naught plus beta 1 x1, so R square of that model is going to tell me how much variability in Y can be explained with respect to variability in x1. But in multiple linear regression, what we do, we keep on adding multiple variables. So you might be thinking, how do we compare two different models? In one model, I might have, y is equals to beta 1 plus beta 2 and up till, let's say, beta 4. And in another model, we will have, y is equals to beta naught plus beta 1 x1 plus so on and so forth up till, let's say, beta 10 x10. So how do we compare these two models, right? Because one model is having lot of more variables. So to compensate this factor, to compare these two different models, we use adjusted R square, right? Adjusted R square is, a better metric than R square, because R square is only going to compare how much your model is good at explaining. Adjusted R square is also going to compensate how many variables you are going to plug in. So if I keep on adding more input variables, if I keep on adding more explanatory variables, my adjusted R square will keep falling down if the explanatory power is not good. So what we need to understand is that I cannot just blindly keep on adding input variables assuming that my model will improve. Yes, it might improve. Let's say when I had four variables, my R square was something like zero point 0.9. And when I added the fifth variable, my R square became 0.91. When I added the sixth variable, my R square became 0.915. So you can see this thing, right? When I keep on adding more variables, my R square is increasing very, very little. So do you really think that having one or two extra variable is good for just a tiny increase in R square? So for that factor, we use adjusted R square, because adjusted R square is going to give us a metric to measure, right, how much it is good. So this is what formula for adjusted R square would look like. 1 minus this entire fraction, 1 minus R square, n minus 1, n minus k minus 1. N is your number of samples. Let's say I have 100 rows, 200 rows. So this n is going to be that. K is going to be the number of explanatory variable. So this is what you should remember. This k is that number of explanatory variable. And that is why if you keep on increasing k, right, if I keep on adding more things, this denominator will keep on decreasing. If denominator keeps on decreasing, then this fraction as a whole will keep on increasing. And when this fraction increases, 1 minus that thing, it will keep on decreasing. That is why it is important. If you want good adjusted R square, your variable should be something less, right? And it's not just that thing. If I add a variable, let's say my old R square is 0.6 and I add a variable, my new R square becomes, let's say, 0.9. So you see there is a big jump. So this variable is valid, right? Then you will see adjusted R square also jumps a lot. But when you add, let's say, new variable and that variable was not really effective, that variable was not even giving any good information, then in that situation, your adjusted R square will not increase that much. It will be very tiny increase. That is why adjusted R square is a better metric to compare, right? We can also take this example. Let's say you are going to give an exam. One student is given 3 hours to complete that exam, and one student is given 5 hours to complete the same exam. So, do you think it's fair to compare these two students? One is given 3 hours and one is given 5 hours. So, to avoid this kind of situation, to make the comparison fair, we use adjusted R square, right? So, basically, we are going to normalize the score of, let's say, the person who was taking 5 hours back to 3 hours, and or you can either normalize the person who was taking 3 hours to 5 hours, and it gives you a fair grounds to compare, right? So, if I have two models, let's say one model is having 5 explanatory variables and another model is having 10 explanatory variable, I would use adjusted R square to compare them, right? So this is how you use adjusted R square. As I've written, these are few important points. Adjusted R square is going to help you in comparing two models with different number of explanatory variable. It will let you decide, should I add this variable or not, right? So this gives you information about how much value addition, basically explanatory power addition, does the new variable bring in, right? Because if you realize that your adjusted R square is not increasing, or let's say it increases very little, then it makes the indication that the variable which you have added just now, it's not that good. You should not add that, right? The idea is if I add one variable, my explanatory power should jump up. So eventually my adjusted R square should also jump up a lot. If the change is very little in adjusted R square, or let's say it remains constant, that means the new variable is not adding any benefit in the model. So we can drop that variable, right? And as you can see, this is modified version of R square, and it is basically adjusted for the number of explanatory variables, right? And adjusted R square will increase only if the new variable significantly improves the model performance. As I said, if the jump is very small in adjusted R square, that means the variable which you have just added, that is not bringing in any benefit, and we can drop that safely. So I hope this adjusted R square formula and explanation is clear. Adjusted R square related questions are asked for sure in quiz 2. So please make sure you revise this concept, remember this formula, and remember these things as well, right? Then there would be a theoretical question. There can be theoretical question based on the understanding of slopes. So we have two type of slopes. First one is known as marginal slope. Second one is partial slope. So when we were dealing with this kind of linear regression model, which is simple linear regression, you had only marginal slope. So this beta 1 which you are seeing here, this is known as marginal. Why do we call this as marginal? Because this slope is going to be, taking account of all the things, all the input variables you have. Here we only have x1. So total effect of predictor on the response variable. So this beta 1 is total effect. But when we come to the partial slope, this beta 1 is not the total effect of just x1. Not total effect of all the variables x1, x2 and all. We are only taking the unique effect of x1. So that is why we say, beta 1 is the change in y. If I change x1 by 1 unit, assuming all other stuff are constant, because we do not want effect of all other variables in the y. So partial slope is there for your multiple linear regression, and this is basically the unique effect of particular predictor on the response variable. So this is for that thing. So beta 1 is partial slope for x1. Beta 2 is partial slope for x2. Or you can say with respect to x2, that would be a better notation. Beta 1 is partial slope with respect to x1. And this is very important. You know, partial and marginal slopes will coincide if your explanatory variable are independent, right? So if I have, let's say, x1, x2, x3 up till xn, all these xi's are independent of each other. What do I mean by independent? The correlation coefficient r square should be 0, right? Do you remember r correlation coefficient? So the r which you have in your correlation, that should be 0 here. So r equals to 0 for your independent variables, right? And this is what we are comparing. We want to see if the input variables x1, x2, x3, these are independent. If these are independent, then partial and marginal slopes will coincide. Maybe this will be much more clear when we visit the path diagram. So this is path diagram. You will have some theoretical explanation about any question. It could be, some paragraph or maybe some diagram, path diagram, and they will ask you some theoretical questions on this thing. So you should understand what is this path diagram. So basically, to diagnose how things are related with each other and how things are changing with respect to each other, we use path diagrams. As the name is clear, it is basically going to give you how things change with respect to one another. So we have x1, x2, x up till xn. So these are all my explanatory variables, or you can say input variables. And this y is what I am observing. This is what my predicted variable is. So if I change x1 by, let's say, something, y also gets affected, because that is why x1 is input, right? Similarly, if I change x2, y also get affected. If I change xn, y also get affected. So here you can see that my x1 is not affecting my x2, right? My x1 is not affecting x3 and so on and so forth. So that is why I don't have arrows here on this side. But what if in this situation we have this kind of scenario where if I change x1 by something, my x2 and x3 or maybe all other variables keep changing, right? So this, to observe this kind of diagnosis, right, if my variables are correlated or not, we use path diagrams. So here you can directly see if I change x1, assuming, let's say, x1 by 1 unit, my y would change by a unit. If I change x2 by 1 unit, y would change by b unit, so on, so forth. So you can do this thing. If I change xn by 1 unit, y would change by n unit. But here, if I change x1, x1 would change y by a unit, but x1 will also change x2, x1 will also change x3, so on, so forth. And these things will in turn change y, right? So there is some direct and indirect combination. And this is what we study in the path diagrams. There are three components. One is direct effect, one is indirect effect, and one is total effect. So direct effect, as you can see, this is very obvious. If I change x1, assuming all other things are constant, this is going to be my direct effect. If I change x1, then y is going to be affected a times, right? If I change x2 by 1 unit, y would be affected b times. If I change x3 by 1 unit, y would be affected c times. So this is the direct effect of these things. But what would be the indirect effect of x1? So if you can see this thing, if I change x1, x1 will directly affect y by a, right? But x1 will also change x2, and x2 will in turn change y. So this indirect path is your indirect effect. And because x1 is changing both these things, so indirect effect would be both D into B plus E into C. So this is your total indirect effect, right? Because if I change x1, x1 will change x2 by D units, and x2 in turn will change it by B units. So that is why D into B. Similarly, E into C. And then I will sum both of these things. So this is what you have. Total effect is going to be direct effect, basically this yellow arrows, and indirect effect is going to be sum of products for these things, B into D plus E into C, right? So you can see this thing. If I change x1 by 1 unit, y gets changed by a unit. But if I change x1 by 1 unit, x2 gets changed by D unit, and then y in turn gets changed by D into B. So this you can similarly write for, if I change x1 by 1 unit, how much my x3 will change and how much y will change. Y will be changing E into C. And therefore, the total indirect effect would be D into B plus E into C. So this is my total indirect effect. Total direct effect is going to be A because I'm only changing x1. So if I only change x1, Y would get changed by A. And total effect would be A plus B into D plus C into E. So this part was my indirect effect and this part was my direct effect. And both things combined would make my total effect. So this is what your path diagram would look like. And the question based on this are quite easy to do. You will directly given the changes, how things happen, and you just need to figure out what kind of change is the question asking you. Now we come to very important part, which is going to be multicollinearity and variation inflation factor. So what do we understand by multicollinearity? We have already studied in stats 1 or stats 2 that when two variables are dependent on each other, they show some correlation. Correlation is basically how one variable changes with respect to another variable, right? And if they are very highly correlated, then that's a problem for us. Why? Because I don't want my x1, x2 and all to be correlated. And if they are perfectly correlated, that means I can predict x1 using x2 or other way around. That is a problem for me, right? Because if I can predict x2 using x1, then why do I really need to keep that in my model, right? Because if I have x1 alone, I can in turn predict x2. So there is no need for storing x2 and using that inside the model. Therefore, multicollinearity is going to be defined this manner. Collinearity refers to a high correlation between two independent variables in a regression model. Multicollinearity is going to be high correlation among three or more variables, right? So if you have multicollinearity, three or more independent values should be correlated with each other. And remember this thing, perfect collinearity violates assumption of ordinary least square. Therefore, if you have a model where there is a perfect collinearity, that means x1 equals to alpha plus alpha 1 x2. So you can predict x1 using x2. Therefore, you would never want this situation. Perfect collinearity is never accepted, right? And how do we measure collinearity? So we can measure collinearity using this metric, which is known as variation inflation factor, VIF. So how do we calculate this variation inflation factor? Variation inflation factor is calculated using this formula, 1 upon 1 minus r square. This denominator which you are seeing here, this is also known as tolerance. So I'm talking about alone this denominator. This denominator is known as tolerance, 1 minus r square. And what is this r square? Is this the r square of the original model? Y is equals to beta 0 plus beta 1 x1 and so on and so forth? No. So if I'm calculating, let's say, variation inflation factor for x5, you can see this example. I have, let's say, 5 input variables, x1, x2, x3, x4, and x5, right? And I want to calculate variation inflation factor for x5, right? Then I would make a separate model where x5 is my target variable, or you can say the predicted variable, and I'm using all other input variables to predict it, x1, x2, x3, and x4. So these model I will use, and the r square of this model will be used in this formula. So this is what you should know. Whenever we are calculating variation inflation factor for some input variable, let's say xi, I would, use r square of the model where this input variable is my predicted part, which I'm trying to predict using all other input variables, right? So let's just go through this example again. If I have 5 input variables, x1, x2, x3, x4, x5, and if I want to calculate the variation inflation factor for x5, basically my model would be this one. x5 is equals to alpha naught plus alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 plus alpha 4 x4. I will calculate r square for this model, and then I will use this r square here in this formula, 1 upon 1 minus r square of this model. So that is why uh, variation inflation factor is calculated using this formula. And how do we interpret variation inflation factor? So if your variation inflation factor is 1, that is a very good sign. That means you have no correlation. If variation inflation factor is between 1 to 5, then there is moderate correlation, and you can kind of accept depending how much strictly you want to be precise. So generally 1 to 5 range is acceptable. But if your variation inflation factor is between 5 to 10, then there is high correlation and you need to cross check. And if your variation inflation factor is above 10, that is extremely problematic, and this kind of model cannot be accepted. This model might be accepted, but you need to diagnose what is the issue, how we can improve these things. So now we must also understand how this VIF affects us. So when you will calculate the standard error in the estimation of this parameter, as I told you, right, we have a very big population. Let's say 1 lakh people, and all that people follow some trend, right? They follow a trend, linear trend, y is equals to beta naught plus beta 1 x1 plus beta 2 x2, so on and so forth. But you will not have access to all these lakh of people. You will get a separate sample, let's say 1,000 people, 100 people, 200 people. Using that sample, you try to estimate these betas, right? So that is what linear regression does. And when we are estimating, there could be some error. So this is basically the standard error in estimation of my parameter beta I. And how does it look like? This is your standard error of the model. This is root n, how many samples you have. And this is standard error, deviation in your input variable x. So this is what your formula looks like. Standard error of model. This is square root of your number of rows, or you can say number of samples. And this thing is standard deviation of that variable, right? How much variation is in this variable. Now, if I have variation inflation factor, this standard error would be increased by under root of variation inflation factor. So that is very problematic, right? Because if my VIF is increased, square root will also increase. And if my square root is increasing, this standard error would also increase. So your standard error is more. And honestly, you never want more standard error. That is why, to keep our standard error in estimation of this parameter to minimum, we want VIF to be minimum. And that is why we always tackle multicollinearity. You cannot just have a model with much higher multicollinearity. So I have listed down some reasons why high VIF would be very problematic. So, if we have this kind of model where the VIF is very high, the coefficients would be unstable, and the estimated coefficients can be unstable and sensitive to small change in data. This means that coefficients might vary widely depending on which variable are included in the model. So your model is not stable. In general, it shows a lot of discrepancy. So you don't want this kind of model. Then we have difficult in interpretation. So, if we have high standard errors, it makes our interpretation very difficult, right? You cannot say that my y is changing with only beta 1, right? Amount, right? We cannot write del y by del x1 is equals to beta 1 because this beta 1 is not a fixed value. It can change. Standard error is very high. So therefore you never want standard error to be high, and if you want to standard error to be low, variation inflation factor also needs to be low. So you can read this thing. Higher standard errors make it more challenging to interpret the significance of individual predictor. A predictor that might be significant in isolation could appear insignificant when considered alongside highly correlated predictors. What does that mean? Let's say I was originally building a model y is equals to beta naught plus beta 1 x1. So this model looks very good, right? But when I go with a model, let's say y is equals to beta naught plus beta 1 x1 plus beta 2 x2, and you realize x2 is highly correlated with x1. So in that scenario, this model would not be very good to interpret because in isolation it was performing good alone, but x2 and x1 are highly correlated. So when two correlated parameters would be used, sorry, two correlated variables would be used, that could be problem. So you can read the others. And how do we tackle high VIF? Basically, you can remove the variable which is having very high collinearity. You can combine the variables together, right? Else you can just apply PCA. These things are not actually in the syllabus of business analytics, but you should know that we need to tackle them. And how do we tackle them? The best one is to remove the variables which are correlated. So let's say I know x1, x2, and x3 are correlated. So I can remove any two, and I will only keep one, right? Because if x1, x2, and x3 are correlated, that means I can use x1 in place of x2 and x3. So that is why the best approach would be removing the variables. Else you can apply these techniques which you would have already studied in machine learning foundation: principal component analysis, regularization technique, combining variables. So you can do all these things. And but removing the other variables, if I have five variables which are highly correlated, I will remove four, right? I'm not going to remove all the five. This is very important. Remember this thing, that we do not remove all the variables. We only remove n minus 1. So if n variables are correlated, I would be removing n minus 1 variables. And again, remember this formula. This is very important because people will ask you questions on this thing. How much my standard error changes? How much my standard error changes when variation inflation drops? So you need to be cautious of this thing, this formula. Standard error in estimation of my parameter beta I is equals to standard error of the model. Root n is basically the number of samples you have, under root of that, 1 upon standard deviation in my parameter xi. So whatever coefficients I'm trying to estimate, the corresponding x variable, I would get the standard deviation. And this is your variation inflation factor, under root of that. So remember this thing. And with this, we are done with the theory of multiple linear regression. I would also make another video, separate video, based on the analysis of, variances, ANOVA, and how we use Excel toolpack, data analysis toolpack, to work on that. But for this, I would suggest to focus on adjusted R square and how do we calculate these values, using the formula. So variation inflation factor, adjusted R square, standard error in the estimation of any parameter, because these are quite common question, and they always check theoretical understanding of adjusted R square. So please go through these points which are here, and also be cautious of this thing: total effect, direct effect, and indirect effect, right? So remember the path diagram. And with this, I think we can conclude the theory part of week 6. I would be coming up with the PYQ video as well as the video for ANOVA. So hope you enjoyed it. Thank you, everyone.